Here's a real item you can buy on Amazon.com. It's called a go-go heel stopper. I'm going to guess that they're used mostly at weddings and graduations. And it's just a little piece of plastic that you can put on your high heels to keep you from sinking into the grass. So the question is, what's the purpose? Do these things change the amount of force that you impress against the ground, or do they change the amount of pressure? Or both? Which is it? When people walk in the snow, they'll often wear specialized snowshoes. What's the point of these snowshoes? Is it to decrease the amount of force that you exert against the ground, or to decrease the amount of pressure? I would argue that wearing those shoes increases the amount of force that you exert against the ground for one simple reason. I think a pair of snowshoes is heavier. I think it weighs more than a pair of sneakers. And so if you stand on the ground with these type of shoes on, you weigh a little bit more than you would if you were standing on the snow in regular tennis shoes or high tops. However, even though the force is ever so slightly larger, the pressure is significantly less, because pressure is just equal to a ratio of force divided by area. So it has to do with the way in which force is distributed across a surface area. And if you have only a slightly larger force due to the fact these shoes are just a little bit heavier than these shoes, but it's spread out over a much bigger surface area than the surface area of the bottom, the soles of the shoes, then it's going to be significantly less pressure, which is the point of these go-go heel stoppers. They don't really change the force. They hardly weigh anything, and so the force that you would exert against the ground is all of your body weight. But if you add that much extra area, which doesn't seem like a lot, but if you compare that area to the area of the spikes on the bottom of these heels, it's large enough that it makes a significant difference. If this is 3 times the surface area, then it would be 1/3 of the pressure exerted against the grass, and therefore keep the heels from sinking in. We often ask if you can handle the pressure. What would you be able to handle better? Leaning against a tree with one thorn, or a tree with many thorns? Probably want this case. How about this? Could you handle the pressure if you put your back against the wall and you had somebody put their flat palm against your chest and lean into you with all their weight? Might be concerned, but you can probably handle the pressure. Would you allow that person to put a knife in between their hand and your chest and still press against you with all of their weight? Well, as long as the knife lays flat, so that force is distributed over the full surface area of the blade, not a problem. I don't think you can handle this type of pressure. When that same amount of force is distributed only against the tip of the knife, the pressure becomes really large because that same amount of force is now distributed over a smaller area. The idea here is that pressure is inversely related to area. So as the area goes down, the pressure goes up given the same amount of force. I actually think we all do pretty well at handling pressure because it's been around us all of our lives. The radius of the Earth is about 4,000 miles. That's a pretty good approximation. So here's a figure that's not properly drawn to scale at all. If the dashed line here represents the upper limit of the atmosphere, then the distance from the surface of the Earth to the top of the atmosphere is about 200 miles. Okay, so 200 miles is a pretty small fraction of 4,000 miles, but in this picture it doesn't look to be that small. So the thickness of the atmosphere has been exaggerated in this diagram. Here's another quantity that's been exaggerated in this diagram, the height of your body. But in any case, let's say that you, standing on the surface of the Earth, the pressure that you've experienced your whole life is force divided by area. The force I'm talking about is the weight of a column of air that sits above your body and extends to the top of the atmosphere. Now, air doesn't seem like it weighs much of anything, but you'd be surprised how heavy air is. Take your refrigerator, for example. A standard size refrigerator You might have a carton of eggs inside the refrigerator. So I can ask this question: what weighs more, the carton of eggs or all of the air inside of your refrigerator? The answer is they're about the same. All of the air inside of a standard size refrigerator would be about the same weight as a full carton of eggs. So imagine a column of air that extends 200 miles high and the weight of all of it pushing down on your body. Well, you've been subjected to that pressure your whole life, so you don't really notice it. We call that atmospheric pressure. What would happen if you were to lay flat on your back instead of standing up? Is that going to be more or less pressure? Because look, it's now a wider column of air. So this much air should weigh more than this much air. But we're not talking about force here, we're talking about pressure. And pressure is force divided by area. So sure enough, all of this air creates for greater force, but then again, by laying on your back, you've created a larger surface area for that air to spread out across. So if the area has increased by the same factor that the force has increased, the pressure has remained constant. So in our next video lesson, we'll investigate or talk about values that we can associate with atmospheric pressure.